So in this problem, we have a bullet that's going to strike block 1, and then after that, it's going to leave block 1, and then causing block 1 to move to the right at a rate of 0.62 as given in the diagram here. And then that bullet is going to embed itself into block 2, causing the system to move to the right. So if you need to, pause the video, read part A, B, and C, and then keep up. All right. The first thing I'd like to point out is that the mass of the bullet is given here in grams. The mass of block 1 is also given in grams, and the mass of the second block is also given in grams. So you need to convert grams into kilograms by dividing all these values by 1,000, because that's the conversion factor. And that, I'm going to go ahead and get started. I want to break this problem up into two parts. The first part is the bullet hitting the block 1, and then the second part is when the bullet strikes block 2. So my work here initially is just going to be when the block leaves bullet 1. Oh, excuse me, not bullet 1, block 1. So my work, I have the momentum of the bullet initially plus the momentum of block 1 initially equals to the final momentum of block of the bullet plus the final momentum of block 1. Here, I'm just going to go ahead and cross out the momentum of block 1 initially because it was sitting at rest. So the only momentum is contributed by the bullet. So here's the mass of the bullet times the velocity of the bullet initially. And that's going to equal to the mass of the bullet times the velocity of the bullet when it exits. And then times the mass of block 1. And then the velocity of block 1 after the bullet leaves it, which is given to us as 0.62 here. Okay, so here I'm just going to do plug and chuck. Mass of the bullet is given. The initial velocity of the bullet is given as 360. Mass of the bullet once again is given. And then here the mass, the velocity of the bullet in the final frame is what I don't know, but I need to figure that out so that I know what it is going to do in the second part of the problem when it strikes block 2. Mass of block 1 is given, and then the velocity of block 1 after the collision is given as 0.62, once again in the diagram there. So the only thing I don't know is how fast the bullet is moving after it leaves block 1, but I can just go ahead and simplify this stuff here. At the left side, if you do it, multiply that, you'll get 1.6704. Here on the right side, 1.163 times 0.62 will give you 0.72106, but you notice I moved that to the left side of the equal sign by subtracting it, so I can find VBF by itself, and therefore, if you simplify the left side, you'll get 0.94934. And then to get VBF by itself, divide both sides by the mass of the bullet, which is 0.00464 there. Okay, and that will leave us with the final velocity of the bullet when it exits block 1, which is 204.6 to the right. And then it's going to be moving at this speed right before it strikes block 2. So this is my final velocity during the first collision, but it will be my initial velocity in the second collision. Okay. So I'm just going to skip a couple lines here. So in the second collision, you have the bullet initially moving. It now has a new initial velocity, which is 204.6, not 360. And then here on the right side of momentum, I have the mass of the bullet plus the mass of block 2. It's written like this in parentheses because now it's embedded, so the masses are added up. And then the final velocity is just VF with no subscripts 1 or 2 or all that good stuff. On the left side, we know all the values. Mass of the bullet is given. The initial velocity of the bullet now, okay, for the second part is 204.6 because that's what we just found in my first part here. And then the mass of the system, the bullet plus block 2 is given. So the only thing I don't know here is the final velocity of the block 2 and the bullet. So I can just go ahead and do a quick math here. Simplify the left side by multiplying. That will give you 0.9493, and then add up the mass of the bullet and block 2, and that'll give you about 1.511. And then to get the final velocity of the second block and the bullet in it, you just divide both sides by 1.511, and that'll leave us with a value of positive 0.628 meters per second. Here the positive sign is included for you because the problem asks for a velocity, and in this particular diagram, block 2 and the bullet itself is moving to the right, so there is the plus sign to indicate direction. Okay. Now, if you don't like breaking them in two parts like that, you can do this. You can treat the whole entire system as a whole, from very beginning to very end. So if you keep up my work here, I think this would be a lot quicker to do in terms of just busy work. All right, so I'm just going to say the initial momentum equals the final momentum, but here I want to look at the initial momentum of just the bullet, and then afterwards you have two things moving. Well, really you have three things moving. You have block 1 moving. You also have block 2 with the bullet inside of it moving. Okay, so I'm on the left side. I'm just going to go ahead and write all three things out. The initial momentum is contributed to three things: the bullet, block 1, and block 2. Likewise, on the right side, I have the bullet, block 1 and block 2. but I am going to cancel out P1i and P2i because initially both those things are stationary, so the only momentum is contributed to the bullet itself. On the right side, you notice, however, I highlighted a couple things for you here. I highlighted the momentum of the bullet final and then the momentum of the second block final. Well, I highlighted because the bullet is going to leave block 1 and then embeds itself into block 2, so these two quantities can be added together. So here is what I did. P1F actually moved down to the front here, so I have the mass of block 1, and then V1F once again is given as 0.62 after the bullet has struck it and left it. Okay, these two highlighted terms, the bullet and block 2, is added together because now the masses are moving together as a whole. So here, if you plug and chuck all your values in, mass of the bullet is given, the initial speed of the bullet from the very beginning of the problem is 360. Mass of block 1 is given, the final velocity of block 1 after the bullet struck it and during the first collision is given as 0.62, and then add up the masses of the bullet and block 2. Okay, I think I might have switched here. The mass of the bullet should be 0.0464 and the mass of block 2 should be 1.506, but it doesn't matter. I mean, so the sum will be the same. All right. Other than that, add things up and then combine like terms. Here I have 1.6704, and then on the right side of the equal sign I have 0.72106. I'm going to combine those two like terms by moving this to the left side, which will cause it to be subtract, or you can say subtract them from both sides, however you want to say it. And then to get F by itself, divide both sides by 1.1064, and then you simplify that, you'll get the same answer as the previous strategy, which is positive 0.628. So once again, I treat this whole entire system as a whole. Okay. I think it's a little less work, but as long as you don't get mixed up in the work here in the third line and fourth line, I think you'll be okay. All right, do whatever your brain processes. Let's go ahead and crack out part B and C. Part B asks us to find the impulse experienced by the bullet and block 1 during the first collision. So impulse by definition is changing momentum. I'm just going to do the bullet first here. So changing momentum of the bullet is going to be final momentum of the bullet minus initial momentum of the bullet. Here, m can be factored out because momentum is just mv, so really it's just m times delta v. Here I move out m, delta v is just v of the bullet final minus v of the bullet initial, and I know all these values already. I know the mass of the bullet is given, I know the final velocity of the bullet is 204.6 after it leaves the block 1, but its initial velocity is 360 before it struck block 1, so therefore if I simplify the parentheses here, it will give me a negative 155.4, and now I can just multiply by that the mass of the bullet, and then the impulse experienced by the bullet is a negative value because it is slowing down. In this case, the force is pointing leftward because it's slowing the object down as it's moving rightward. So the magnitude is 0.721, but impulse is a vector, so make sure you put the negative sign in the front there. All right, so we know that already. Now, without really doing work for block 1, we know that the answer for block 1 is just the opposite of this. The impulse experienced by the bullet is just the opposite of the block 1, okay? But I'll do it anyway just to show you that it comes out the same magnitude, just opposite direction. So if I just apply the same function here, impulse, once again, changing momentum, block 1 is equal to the final momentum of block 1 minus the initial momentum of block 1. But block 1 was initially at rest, so I'm actually going to go ahead and cross this out. V1i for block 1 is at rest, so that's just kind of redundant there, but I wrote it out for you just kind of see so you can cancel things out. Mass 1 is given. V1F we already know from the diagram. The diagram says that after the bullet leaves it, it's moving at a rate of 0.62, so we didn't have to do anything except for do a little plug and chug. The mass of block 1 is given. The final velocity of block 1 is also given. So here, if you do that, you'll get a positive value, and if you punch it in your calculator, you get the same magnitude. So I can see here, the impulse experienced by the bullet and block is the same magnitude, just opposite in direction. Okay, so keep that concept in mind. All right, let's go ahead and do part C. Part C asks us to find the ratio of the total kinetic energy after the collision to that before the collision. So here's what I did. I'm just going to write KEF divided by KEI because it wants KEF relative to KEI. In the final frame, you have three things moving. You have the block 1 here moving to the right at 0.62. You also have the bullet and block 2 moving together at the same velocity. So here's what I did. This is KE for the block 1. So it just be 1/2 M1 V1F square. And then I added everything together here. So it'd be 1/2 times the mass of the bullet plus block 2 because it moves together as one times the final speed there, and we're going to square that. And then, but initially, the only kinetic energy came from the mass of the bullet and then the speed of the bullet. Okay, so I'm going to cancel the 1/2 out because there's a term everywhere. Oops, that 1/2 should have been canceled out too. Maybe my animation is just late. But anyways, if you plug in mass 1, which is given the final velocity or the final speed here, because this is KE, so I can just use speed. The final speed of V1F is given in the diagram as 0.62. Mass of the bullet, mass of block 2 is also given. Add those two up, you get 1.5106. And then the final speed of block 2 plus the bullet was already calculated to be 0.628. So we need to pause the video and go back once again. After the second collision, the bullet and block 2 moves off to the right at a rate of 0.628 meters per second. And then on the bottom, it would just be the mass of the bullet, because the initial kinetic energy is just only from the bullet. And then the initial speed of the bullet was given as 360. I'm going to square that. So hopefully my calculator works good here. If you simplify all this, you should get about 0.00173. And that would be your answer for this particular problem. Okay, I hope that helps. Stay nerdy, don't be wired.